Hello, everyone. So during the last two class hours, we've discussed two important types of linear programming problems. One is the transportation problem, and the second type is the assignment problem. And last time we also talked about the Hungarian algorithm as an efficient solution approach for the assignment problem. And today, I'm going to give you two examples, one for the transportation problem and the other for the assignment problem. Okay, so let me share my screen first. Okay, so, and okay, so okay, so this is the first example for today. So let's imagine that you are working for a major US airline company as an operations research analyst, okay? And your boss came in and asked you to develop a crew scheduling, okay, plan. And your boss wants to know how to effectively assign the flights to the crews to minimize the total layover time, okay? And the summary of the information that your boss provided includes and the airline operates 7 different flights daily between the New York City and Chicago, okay? And the crews are based on either city and fly to and from the other city each day, okay? And the restrictions we need to consider is that each of the airline's crew live either in Chicago or in New York City. And each city, a crew must fly one New York to Chicago flight and one Chicago to New York flight, okay? And there must be at least 1 hour layover time between the flights. And at the end of the day, the crew must be in its home city, okay? So these are the given information and we must fulfill these requirements, okay? And the airline company wants to assign the flights to the crews to minimize the total layover time, okay? And so they want to know how many crews should be based on each city, okay? So let's keep in mind that the airline company wants to minimize the total layover time. Intuitively, I do make a table of layover time for flight pairs, okay? So, okay, so based on the given information, here's the table which shows the layover time for the flight pairs, okay? Okay, let me disable my camera so you're gonna see the full screen. Okay, so here's the thing. Excuse Okay, so these pairs are flown by a Chicago-based crew. Okay. So, so for example, this number 8, this came from the layover time for the Chicago-based crew, right? So he takes flight number 1 to New York City. So he takes the flight number 1, right, which is this one, to New York City. So he will arrive New York City at 10 o'clock in the morning. Is that right? And he will take flight number 7 because of this, right? At 6 o'clock in the evening, right? To come back to Chicago, okay? This. So in this case, the layover time would be 8 hours, right? From 10 o'clock in the morning until 6 o'clock in the evening, right? So that's why the layover time of 8 o'clock has been obtained for this pair, okay? Oh, that's what I explained you. So first he take the airplane, number 1, flight number 1 to New York City. So he will arrive at 10 o'clock in the morning, right? And then he will take flight number 7, right, at 6 p.m. to come back to his home city, which is Chicago, right? So that's why we got the 8 hours of layover time. Okay, then what about this? How'd you get this number 3, the layover time of 3 hours? Again, this layover time is for the Chicago-based crew, right? So he takes flight number 2 to New York City. So he will arrive New York City at 1 o'clock in the afternoon, right? And then he will take flight number 6, right? At 4 o'clock in the afternoon to come back to Chicago, right? So the layover time would be 3 hours, right? From 1 o'clock in the afternoon until 4 o'clock in the afternoon, right? So likewise, all the other cells in this area, we can compute layover times, okay? Like this. Okay, next, these pairs flown by a New York-based crew. So, for example, how would you get this layover time of 2 hours? What happened if this is the case of Chicago-based crew then? Then he takes flight number 3 to New York, right? So he will arrive New York at 4 o'clock in the afternoon, right? And then he will take flight number 2 at 8 o'clock the next day in the morning, right? And actually this violates one of the given restriction. What is that? according to the problem description, each day a crew must fly one New York, Chicago, and one Chicago to New York flight. And it also violates another restriction that at the end of the day, the crew must be in his home city. Is that correct? So this value too cannot be obtained. So for this value, it must be the case of New York-based crew. Okay. So in this case, he takes the flight number 2 to Chicago first, right? So he will arrive Chicago at 10 o'clock in the morning, right? And then he will take flight number 3 at noon to come back to New York City, which is his hometown, okay? So in this case, the layover time would be 2 hours from 10 o'clock in the morning until the noon, right? So that's why we obtain this 2 hours of layover time for this pair. Okay, then let's try to get one more. Let's think about how we can get this layover time of 8 hours. So first, he takes flight number 3, right, to Chicago. So he will arrive Chicago at noon, right? And then he will take flight number 7, which is at 8 o'clock at night to come back to New York City. So in this case, the layover time would be 8 hours from noon to 8 p.m. Such a long period of time. Right? So similarly, we could obtain the layover times for the rest of these cells in this area, okay? So yeah, I want you to pause the lecture video now and then try to obtain some of these other values to make sure you understand how to get these matrix values, okay? Okay, also let you know that all of these pairs are invisible, impossible, okay? So for example, if this is the, if this pair is the case of Chicago-based crew, then he arrives New York City at 1 p.m., right? Through flight number 2, right? And then he is supposed to take flight number 3 the next day at 10 o'clock in the morning to come back to Chicago. And of course, this violates the restriction, given restriction that each day the crew must fly 1 New York to Chicago and 1 Chicago to New York flight, right? And also violate the another restriction that a crew must be in his home city at the end of each day. So this should be infeasible, okay? So what if this is the case of New York City based cruise? Similarly, he arrives Chicago at noon, right? Through flight number 3. And then he's supposed to take flight number 2 the next day at 9 o'clock in the morning, right? To come back to his hometown, New York City. Again, this violates two restrictions, right? At the end of the day, crew must be in his home city, but he's not, right? And each day, he must fly one New York City, New York to Chicago, and one Chicago to New York flight, but he didn't, right? So obviously it is impossible. So that's why I put plus infinite, very large number, to prevent any assignment on this pair, okay? Prevent from any assignment on this pair. Okay, so let's get back to the original table. Okay. Okay, so this is the layover time for flight pairs. So using this table, let's use the Hungarian algorithm to get the optimal assignment plan. Okay, so let me open up the Excel spreadsheet. So I can work it out. Okay, so this Excel. Okay, and also I'm going to zoom in just a little bit. Okay, this is big enough. Right. Okay, so so we have 7 by 7 matrix, right? So that's gonna be like this, right? 7 by 7 matrix. And we have 2, 4, 6, 8, 1, 3, 5, and 2. And then right here we have 3, 2. Oh, sorry. It's going to be 2. We have 3, 2. Sorry, it's 3, 2. 6, 5, 3, 1. Sorry, I have to move this. Okay, and then we have 8, 7, 5, 3, 1, 10, 9, 7, 5, 3, 1, 11, 10, 8, 6, 4, 2, right? Okay. What about this area? These are impossible pair, right? So in that case, I'm gonna put a suitably large number. So how about 9,999? Okay. I'm gonna use this number. So that is relatively larger number than the layover times that we computed, right? So I'm gonna outline, okay, like this. Okay, so this is going to be our initial cost matrix then for the Hungarian algorithm. Okay. So let me bring up what is the Hungarian algorithm. We talked about it earlier, right? Okay, so this screen summarizes the Hungarian algorithm, right? So the very first step is to make sure the given cost matrix is standardized, right? So we just count the total number of rows. In our case is 7 is equal to the total number of columns. So we also have 7 columns. So our step number 0 has already been taken care of, right? So we don't need to do anything for that. So we are safe to move forward to step number 1, which is row reduction. Okay, so I'm going to use the full screen for that. So what is the row reduction? We need to identify the minimum number for each row and then subtract the same number, same number from each cell, right? In the entire row. So here, what is the minimum number among these 7 values? It's 2, and we're going to do the same thing. So those are the minimum values for each row. And we are going to subtract this amount from each cells of each row, right? So in order to do that, let me just copy this minimum value. For the easy computation, okay? So those are the minimum values. And let me just adjust the column width so that I can show you. The cost matrix, sorry. How much, how many? 1, 2, 3, 4, 5, 6, 7. Okay, now it should be okay. So this value is going to be 9,999 minus this, right? Okay, so we're going to do the same computation. So we'll just copy and paste. So this is our new cost matrix. Okay, so let me just have the boundary side borders like that. Okay. So, and then now we're gonna copy in here. This is gonna be this value. And this, right? So these two matrices are identical, okay? Now I'm going to conduct the column reduction. So as we did, similarly, we're going to find the smallest value for each column. And then we're going to subtract, we're going to reduce the same amount in that column, okay, by the same amount. So first I'm going to identify the minimum value for each column. And then I'm going to just copy that. Okay, so we can do the computation. Is minus minimum value, right? And then this, right? So again, I'm gonna copy the same value. Okay, so this is it. So this matrix is after the conducting the row reduction, and then we also got this matrix resulting from the column reduction, right? Which is exactly same as this, right? And right now we need to perform the step number 3 of the Hungarian algorithm. What is that? We need to find the smallest, the minimum number of lines that can cover every zeros, right? In this cost matrix. So how many lines do we need? But remember, we need to identify the minimum number of lines, right? Of course, with 7 lines, you can cover every zeros, right? In this cost matrix. But we do need to find the minimum number of lines. So okay, because third row has 3 zeros, so I would choose this. But you don't need to, okay? There's going to be multiple different ways to cover every zero with the same number of lines. But I'm going to draw another line here. And then I'm going to draw another line here and here. and here. So I just draw how many? 5 different lines, right? And then with these 5 lines, all of 0 can be covered, right? Okay, so this minimum number of lines is 5. So minimum number of lines is 5, right? Which is not equal to the total number of rows or the column, which is 7, right? So these two numbers are not equal. So what you need is to move on to the next step, step number 4, which is we need to locate the smallest unlined cost, right? So what is the smallest unlined cost then? I believe 2 is the smallest unlined cost right here, okay? So this is the minimum unlined cost. So this amount of 2 will be subtracted from every unlined area, right? Right here and here. And then added to the intersection of these 5 lines. So we're gonna add 2 to these 6 different locations, okay? That's what you're going to do. So let's do that. Next one will be, this will be this minus 2, right? And then this will be the same, right? I'm going to just remove the color. Oh. Let me adjust the column width a little bit. Oh, I think, okay, that'll be good enough, looks like. And then what about this area? We're going to add the value 2, right? This is going to be this plus 2 as well. And I'm going to copy the same formula, just adding 2, right? And here. And what about here? So I'm going to copy and paste down here. Okay. So just make sure we're going to have additional 0 down here, right? Because this amount, the minimum unlined cost, has been subtracted from every unlined area, right? Right here and here and here. Okay. So it's subtracted. How come I have, oh, it's gonna be negative 2, not the positive 2. And this one too. How about this? Yeah, I got the right calculation. Okay. Now we need to add the same amount to this 6th location. That is the intersection area, right? Of these 5 different lines. So here you're going to have the original value plus the minimum unlined cost, which is 2. Okay. And then we're going to do the same thing down here and all of these 6 areas, right? And all the other areas remains the same. So I'm gonna just copy from the previous cost matrix. So just copy, paste, okay? So I'm gonna copy and paste here. And also I'm gonna copy this, paste down here. Okay, so let me just double check. So we got the same value here and here, and this 6, right? And these 2 are also same as this. Okay. Okay. So we've done the step number 4, and then now we need to go back to step number 3. Again, we need to identify the minimum number of lines required to cover all of the zeros in this reduced cost matrix. Okay. So obviously, we need to cover this value, right? In addition to these five different lines. Or we need to think about if there is other way. For example, if there is a way to cover all of the zero with using only 5 different lines. Do we have that? So I'm gonna draw this line. And this time I'm gonna just draw this. Okay. And I'm gonna draw this 3 lines, 4 lines. And 5 different lines. Okay, see, with another 5 lines, we are able to cover every zeros in this reduced cost matrix. Okay. Okay, so again, we need to see the minimum number of lines that we identified is equal to the total number of rows or the columns. So again, here, minimum number of lines, so 5, but the total number of rows or columns are 7. Okay. So these are not equal. These two numbers are not equal. So again, we need to identify the minimum aligned cost, right? So this time, again, the minimum aligned cost would be 2 up here, right? So we're gonna subtract this amount of 2 from every aligned area, right? Here and here, and then add the same amount to the intersection of these 5 different lines, okay? So let's do that. So in this 4 area, we're gonna add the value of 2, right? So this is gonna be original value plus 2. And we're gonna do the same thing, right? But we're gonna subtract the same amount in this area, right? So this is gonna be same as the original value minus minimum aligned cost of 2. And we're gonna have the same value down here, same computation. And I'm gonna just copy and paste and drag it. Copy, paste. And I'm going to copy and paste. Okay. So let's just make sure if we did this computation correctly. So we subtracted 2 from the aligned area. So these numbers looks okay and okay, and these are okay, and these are okay as well. Now all the other areas remains the same. Okay, so we're gonna just copy from the previous cost matrix. So I'm gonna copy and paste like this, and then also copy, paste. Okay. Now again, we need to identify the minimum number of lines that can cover every zeros in this reduced cost matrix. Okay. So how many lines are required? So what is that? It's going to be same as this, right? Okay. So I'm going to draw this line because it has 3 zeros in it. And then I'm going to draw this because there are 2 zeros and another 2 zeros. I'm going to draw this line. And what about this? I think we need 2 more, right? So let me just draw this vertical line. So I use 6 different lines, right? So minimum number of lines this time would be 6. But still, 6 is not equal to 7, which is the total number of rows or the column, right? Again, we need to identify the minimum aligned cost, right? And I believe that's going to be 2, right? Those are the minimum aligned cost. So this same amount will be subtracted from this aligned area and then added to the intersection area, okay? So here, the first element should be this minus the minimum aligned cost of 2, right? And then I'm going to copy the same formula and paste it down here, and also do the same thing, right? Like here. And then intersection area is right here, right? So we're gonna add the value of 2 to this area. That's gonna be the previous value plus minimum aligned cost of 2, right? Like that. And all the other areas right here and here and even here remains the same. So that's going to be just this, right? And I'm going to copy and paste it. Like that. Okay. Now, again, we need to identify the minimum number of lines required to cover every zeros in this reduced cost matrix. So how many lines do we need? 6 lines or 7 lines? Let's find out. So I'm going to draw this because there are 4 zeros, right? So 1 and 2 and okay, maybe 3 this way and 4 and 5. But we need one more, right, to cover this 0. So I draw 6 lines, right? Okay. So the minimum number of lines, so 6. And which is not equal to the total number of rows or the columns, which are 7, right? So again, we need to identify the minimum aligned cost. That's going to be 2, right? So these are the minimum aligned cost. So we are going to subtract the same amount from the aligned area, which is here and here. But we're going to add 2 to this intersection of these 6 lines, right? So this one is going to be original value plus minimum aligned cost of 2. So I'm going to copy, paste, right? But here, this minus the minimum aligned value, which is 2, right? So I'm going to copy and paste. Also, I'm going to paste right here. And all the other values remains the same. So I'm going to copy from the previous matrix. Remove the color. Okay, and copy, paste, and copy and paste. Okay, now again, we need to identify the minimum number of lines required to cover every zeros in this matrix. So I'm going to draw 1. And the second line. And third one. And the fourth one. And fifth one. So it looks like we do need 7 lines this time, right? And this one as well, right? Let me double check if 6 line can cover every 0. So if I draw this 1, 2, 3, 4, 5, 6, 7. Yeah, I don't think 6 line can cover every zeros at the moment. So I believe the minimum number of lines required to cover every 0 should be 7. And this value is equal to the total number of rows or the column, which is 7, right? So I believe with this reduced cost matrix, we should be able to do the 0 cost assignment, okay? So let me copy all of these values. so that I can show you the zero cost assignment. Okay. So for the zero cost assignment, you need to identify the location of zero that appears only once for each row or each column. Where do we have? I think this one only appears once in the last column, right? So we need to choose that. And then you need to cross out the same columns and row, right? To prevent further assignment from that row and the column. Okay. So right now, this is the only zero, right? Appears in the first row. So we gotta choose this. Oh, so I'm gonna use red color, and then again cross out same column and same row. Okay, like this. Okay. Now, looks like we do have multiple options, right? Because there is no zero appears only once for each columns or row. So in this case, you need to arbitrarily choose 1, 0. Okay, so I'm gonna choose this. Okay. And then cross out this. And also cross out this. And again, we do have multiple options available. So I'm gonna just choose this. And then I'm gonna arbitrarily choose this again. And cross out this and this, right? And still we have 2 different options, right? For example, if you choose this, you gotta choose this. If you choose this, you gotta choose this, right? So let me go with this, just arbitrarily. And then this, we're gonna cross out, right? And this too. And you gotta pick this. It's leftover, right? Okay, so that's gonna be the one of the possible zero cost assignment. Okay. So in this case, what you need is just go back to the original matrix. Which is this, right? To get the total layover time, right? So we need to pick here, right? Same location. And then this one, right? And then this one, this one, this one, and this one, and this one, right? So if you add up these 7 different numbers, that will give you the total layover time. So the minimum layover times gonna be sum of this, 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 and this. Oh, not this one. I have to take this out, right? So how much is that? It's going to be 25 hours. So because this airline company want to make sure to get the minimum layover time. So that's going to be the answer, okay? And if you pick this schedule like this way, okay? Okay, so that's the assignment example problem for today. And let's go back to our PowerPoint slide so that we can move on to the next example. Okay, so this example is for the transportation problem, actually. So now I want you to pause the lecture video and please try to work on it by yourself, and then come back whenever you're ready, okay? So that we can save some recording time, okay? Okay, so as you may notice, this example is very similar to the bank example that we discussed earlier. So in that bank example, bank has two different sites and they process 3 different types of checks. Do you remember that, right? So while building the transportation parameter table for that problem, we considered the 2 processing sites as the sources and the check types to be the destinations. So similarly, for this example, let's consider the 5 plants as the sources and the actually 3 different new products to be the destinations, okay? So with keeping this in mind, let's build a transportation parameter table, okay? So again, I'm going to use Excel spreadsheet then. Okay. Well, probably better to use Microsoft Word. Okay, so I think this is good. Okay, so we are going to build a transportation table, transportation parameter table. So it's going to be something like this. I'm gonna, okay, this way. So each row represents the sources. Okay, so that's going to be the plant. Plant number 1, 2, 3, 4, and 5. Okay, and then each column represents the destinations. So in our case, the new product, okay? So we have 3 different products considered, okay? And I'm gonna put the supply amount in the last column. And then I'm gonna put the demand amount, the last row, okay? This is our transportation parameter table, okay, that we are going to build on. So here, what is the supply amount then? According to the problem description, the daily production capacity for each plant is given as 400, 600, and 400, 600, and 1,000 units, right? Right here. Right? So I'm going to put them in right here. 400, 600, 400, and 600, and then 1,000. Okay, like that. And the sales forecast indicates 600 and 1,800 units of each product should be produced daily, right? So we are going to put those numbers from here to right here. Demand amount 600,000, and then 800. Right? Okay. So in this transportation table, what would be the unit transportation cost? That's going to be the unit manufacturing cost, right? So we just need to use the given unit manufacturing cost for each product in here, this area. Okay. So that's going to be 31, 29, 32, 28, and 29, right? From here for the first product, right? And the second product is going to be here, right? So we're going to put that number 45, 41, 46, 42, and 43, right? And for product number 3, that's going to be 38, 35, 40, right? 38 and 35 and 40. But it does say plant number 4 and 5 do not have the capability for producing the product number 3. Okay. So how do you address this in this parameter table? Right here. I do put M. M stands for relatively big number. Big number. Okay. So like we can use 1 million, for example. Okay. For example, 1 million. Okay. So in the actual formulation that you're going to use, It's going to be minimize 31 x11 plus 45 x12 plus 38 x13, right? Plus the next row all the way up to, let's say, 28 x41 42 x42, and then instead of m you're going to use 1 million times x43 plus same thing 29 x51 43 x52 plus again 1 million times x53. That's going to be the objective function of this example number 2, right? And then, we need to construct the supply constraint, the demand constraint, right? For the supply constraint, for each supply point, right? For each sources, you need to add up the x variables, right? So it's going to be x11 plus x12 plus x13. It's going to be less than equal to the available capacity, which is 400. Right? And you're going to do the same thing 4 more times, right? So if I do that one more time, 2, 1, 2, 2, 2, 3 should be less than equal to 600, right? And you need 2 more, right? No, actually 3 more constraints like that. So those are the supply constraints, right? And then our demand constraint should be for each destination, for each product, right? We have 3 different products, so you're going to have 3 different demand constraints for each column, right? So that's going to be x11 plus x21, x31, x41, x51 should be greater than or equal to 600, right? 600. That's our first demand constraint. And you need 2 more for the second column and the third column, right? So you're going to have 2 more demand constraints. And of course, you need to add sign restriction for every x variable, right? For every I and j values, right? So combined together, this is going to be the complete LP model. Okay. Of course, I values goes from 1, 2, 3, 4, 5, right? And j goes from 1, 2, 3, right? So I think that's what I need, right? So of course, if you use Lindo or Lingo that we talked about earlier, then you should be able to get the optimal solution right away. Okay. Okay, so that's all for today. So far we've talked about the LP modeling techniques with graphical method And also, as the typical example for linear programming, we talked about transportation and assignment problem with several example problems. So next time, I think we're going to move to the new topic, which is about the project scheduling. Specifically, we are going to talk about the CPM. Okay. Okay, thank you. I will see you next time. Bye-bye.